Oh, I said sound. Yes. Sorry, I was muted. Sounds good.
We'll wait another minute before we get started. Okay, everyone, welcome to our bi-weekly Green Bank Telescope Community Zoom. Karen O'Neill, the Observatory Director, is unable to attend just now. She may join us in a little bit. And so I'm Jay Lockman, and I'll be the host for today's science talk. Let me just mention a little bit of observatory news before we begin, because yesterday it was announced that Karen O'Neill's successor as Director of the Green Bank Observatory will be Dr. Jim Jackson. Many of you may have known him from his work at Boston University and in Australia, and he's most recently been associated with the Sophia Observatory. And we believe he will be joining the Green Bank Observatory sometime in mid-October. That's all of the news that I know of. And in the absence of Karen O'Neill, we'll go ahead with our science presentation today, which is by Michael Busch of Johns Hopkins University, and he'll be talking about dark molecular gas and OH observations in the Milky Way. And if you have questions, please use the Q&A box in the lower right hand of the screen, and I'll field those for Michael when he's done his talk. Take it away, Michael.
Thank you, Jay. Let me just share. All right, I think this looks fine. Yes, hi everyone, my name is Michael Busch. I'm a NSF fellow at Johns Hopkins University. And Green Bank is sort of my secondary science home. So a lot of my work is done with the Green Bank telescope. And a lot of my time is spent at Green Bank convincing the GBT science staff that my results are real. So I think we've gotten there. So I'll be talking about faint 18 centimeter OH emission surveys with the Green Bank telescope and what we've learned in how that reveals a type of dark molecular gas that is not seen by CO. And so I just want to mention that a lot of the lion's share of this work was done with Ronald J. Allen, who unfortunately passed away last year. He was my PhD advisor. And so I'm now working with Joshua Peak at Space Telescope. Some of my collaborators include David E. Hogg of NREO. He's at Charlottesville, and Philip Engelke, who is Ron's previous student, who now works at Frontier Technologies. So he's in industry and does something that is super secret that I can't talk about. Right, so to set the stage in my talk and set the stage for these OH observations, I'd like to just show you how I think of our galaxy and the interstellar medium and the phases in which we usually talk about. And what I am most interested in is in the transition between the atomic gas and the molecular gas. Where do atoms transition to molecules, and how do the molecules regulate star formation, and where does that start? So normally we think of molecules as being traced by the CO molecule. As we all probably know, H2 is invisible in the bulk of the interstellar medium. And so we use tracer molecules to try to figure out where the molecular gas actually is. And we either, in the case of CO, use a mass to light ratio like XCO, or in the case of OH, you can use an abundance ratio because it's optically thin. So about 20 or 15 years ago now, there's been this observational mystery that has been referred to as dark gas or CO dark gas. And basically, indirect tracers of the total gas column have shown that there's an extra component of gas that is not traced by either H1 or CO. And this has been seen in Planck as well. So you can see here that there, as you increase tau, so cloud depth, there appears to be a transition zone where there's excess dust emission that is not linearly correlated with what gas that is traced by CO and H1. So there's a lot of questions about this dark gas. What is it? Is it atoms and molecules? There's been a lot of papers saying that it's optically thick H1. There's been other papers saying that it isn't, which is the camp I'm in. How much of this gas is there? What is the baryonic mass of the galaxy because of this dark gas? Where is it? It's probably a very large volume since it's probably this diffuse gases. You can see this gamma ray distribution. And what's the environment? What's the densities, temperatures, et cetera. So I use 18 centimeter OH as a new old tracer of molecular gas. It's actually the first molecule detected in the radio regime by Weinreb and Barrett. Barrett was Ron's PhD advisor, so there's some pedigree here. And so OH has been shown to trace the CO dark gas in a few but very important surveys. To the right here, I'm showing Arecibo observations of the Taurus molecular cloud. You can see very clearly the transition between the CO bright gas to the CO dark gas. And so these beam widths here are OH observations, and the grayscale is the CO, and you can see where it transitions. And so this is a very small spatial scale. And things I'm going to talk about are very large spatial scale in the coming slides. So the advantages of OH is that its critical density is much lower than CO. It's at 1 particle per cubic centimeter. So the levels will probably always be populated in the interstellar medium. It's optically thin, so there's no X factor required. We could just use an abundance ratio. The caveat is the emission is faint, and so that makes the observations very hard. If you're used to the PDR schematic of molecular clouds, I can show you something like this. So basically, you have your atoms. As you go into the cloud, you start to form H2. Hydrides start to form. As you go deeper in the cloud, your O starts going to CO. But basically, we believe there's this region where OH exists, and that CO is either photodissociated or isn't collisionally excited enough. Here's a picture of me and Ron last time we were at Green Bank about 2 years ago. So Ron started this whole enterprise with the Green Bank telescope to look for this faint OH emission in the outer galaxy. And these X's here correspond to his first OH survey, the GBT in 2015. And this was my first project in 2019 with the 1 square degree, which is filled in, 9 beam widths by 9 beam widths OH surveys. So these are the results I'll show in the next 2 slides. But I just want to say that the outer galaxy is a very good place for OH emission surveys. The background continuum is very low. The OH excitation temperature is also very low. So in order to see the emission, you need to have a very low background. So towards the inner galaxy, this is a known problem. Towards the outer galaxies, you get, as you cross features and spiral arms, you get very discrete peaks. So you can say something about where this gas is or what spur or arm this is, although distances are still relatively unknown at a plus or minus like 1 kiloparsec scale. So this is, but you still see there's no need for Gaussian decomposition. You can figure Gaussian to this and get some good results. So on the left here is a scatter plot of CO and OH in the original survey that Ron did in 2015. And on the right, basically I zoomed in and just picked out the Perseus features and plotted the profile integrals between OH and CO. And as you can see, there's a regime where CO and OH are kind of linearly correlated, so they're tracing the same content, but there's also a regime where there's OH bright and CO dark gas kind of everywhere. And so this is what you see when you plot it as a grid. So we have this 1 square degree, each box on the side's about 7 parsecs at the GBT scale, the beam size scale. And on the left here, you see your classical CO clumps, but then you see a dearth of CO everywhere outside these clumps. And on the right, you see that there's OH basically everywhere. The idea of this project was to sort of see where does the OH end, where does the OH start. But what we really found is that there was OH everywhere. So we just concluded that the structure appears ubiquitous. And when we try to model the OH column densities and CO profile integrals with some diffuse cloud models, we realized that our results, as we plotted them on this grid, were consistent with the explanation that the value density implies that there's some CO sensitivity cutoff because of the critical density of CO is about 3 orders of magnitude higher than OH. And so this is the summary of that project, that the CO bright mean volume density is higher than the CO dark mean volume density, and that the OH structure appears consistent with the morphological description of dark gas. So just moving on from that, I'd like to talk about my recent paper, which is discovering the disk of dark molecular gas in the outer galaxy. So just to remind you what the picture is with, between the atoms and molecules here. Here is M51 and CO, and as these are not spectra M51. This is spectra of the Milky Way. The right is M51, just as an illustration of what you might expect as you point towards the outer galaxy. In H1, you have emission everywhere, and there's narrow peaks corresponding to higher density areas. In OH, this is a 2-hour integration. You see peaks at the same areas where the H1 peaks as well. And in CO, in this random sight line, you see nothing. So basically, these are both molecular tracers. This is an illustration of CO dark gas. And you see your atoms are everywhere along the line of sight. And you see this nice little tail off as you get out into the very far outer galaxy. So in 2016, in a particularly deep profile, we had 6 hours at one sight line because we had extra time. Philip Engelke realized that there was this bump in the middle of the spectra, and what we saw was something that looked like this, that there was OH emission throughout the entire outer galaxy. And just to orient you, 0 is around the sun, -50, -60 is Perseus arm area, -80 is like the outer arm area, and -125 is out in the boondocks, a very far outer galaxy. So this is like tens of kiloparsecs, right? And so we were immediately convinced we had done something horribly wrong because we were seeing molecules everywhere. And why was this so difficult? Just as an aside, I'm not sure if everyone's a radio astronomer, but spectroscopic measurements are usually done with difference, with some type of difference measurement. So usually there's observations that are position switched. So you look at your source, and then you look off your source, and you difference those two spectra. Well, because we had seen that OH was basically everywhere, we chose to go with frequency switching because we weren't sure where we could look at a position and not have OH. The only problem with this is because we chose in-band frequency switching so that we don't actually lose time and you could shift things and average, you introduce negative signals into your bandpass. And our signal was quite broad. And so this is what you get when you load up the spectra and GBT-IDL and try to fit the baseline. It's crazy because you have 2 signals from OH. The OH ground state has actually 4 lines, but only the main lines are bright enough to be seen in thermal emission. Signal 1 here corresponds to the 1667 megahertz line. Signal 2 corresponds to 1665 megahertz line. The 1665 should be 5/9 weaker. So that's why it looks like it's not even there. But what I'm trying to show here is that there's ghosts in the spectra as well. And so the bandpass that you could fit to fit your polynomial is this discontinuous areas of free signal. And we really don't like higher order polynomial fits. So we took an extra couple of years to figure out this is actually real. So what we did was we built 2 different pipelines, and then we finally chose to use the 20 meter at Green Bank to take another spectra around the same area. And so we bought 100 hours of telescope time, and we took 50 hours at 2 positions. We found the signal in both of those, so we just averaged them together. And so this, we relied on the stability of the radiometer, and we didn't actually do frequency switching or position switching. So this was a total power measurement. And so it's much cleaner because there's no ghosts, and so we could fit a 4th order polynomial. And so the signal still appears. So this really told us that this was something real, not introduced by like high order polynomial fits. And so that's where we were when we announced that this is a real thing. So we have 2 lines and 2 different telescopes at 2 different angular scales at many different positions. And the conclusion we came to is that this is a galactic disk of diffuse H2 co-spatial with the atomic phase. And so you can look at those results in Busch et al. 2021. As an additional test for large scale structure, why am I saying that this is a disk? Well, we know how H1 behaves in the galaxy. We found this structure around a longitude of 108, and we know that as you go towards 180, your emission should scrunch to 0. And so that's exactly what happened. We asked for filler time, and we took spectra at 10-degree increments, and we found that the OH emission also scrunched towards zero. It followed the H1 very nicely. And so this is what pretty much the nail in the coffin that convinced us that this is a large-scale structure towards the outer galaxy. And if you change to physical units, or what I call proton space, it's just asking if you believe the assumptions that people are using, and you go to proton column density per 1 kilometer a second channel, what do you get? And so what you basically see is that the mass of protons, or the amount of protons traced by the OH, by assuming that the OH is tracing H2, is about equal to the H1. And so that's similar to estimates from dust and gamma rays, but crucially, OH provides a radial velocity information that we never had before that allows us to assert that the form of the dark H2 is like a disk in the outer galaxy. So if there's this large OH emission towards our outer galaxy, one natural extension is, well, can we look at another galaxy and find this large scale OH emission in a nearby galaxy? So in response to the observatory's call for proposals during COVID, Ron and I had submitted we asked for 80 hours for a pilot search for OH in Andromeda. And so this is the H1 map from Effelsberg of Andromeda. These are 2 blind pointings we did for about 20 hours each. And I'll show you that in the pink pointing, we found something, and the yellow one is a OH non-detection that I'll also show. And right, yeah, this is about 60 arc minutes from the center, and it's astronomically interesting because it's outside the CO molecular ring of Andromeda. So this is kind of analogous to outside the solar circle where the CO drops off. Right, and so here we're in the southern ring. So basically the question is, does OH show that there's a H2 column that is not being traced by CO that is around the same level as the H1? And there's a lot of literature on the OH to H2 ratio. Unfortunately, a lot of those are in the solar neighborhood. So, you might think that this ratio evolves with metallicity or volume densities, and that's probably true. We just don't have a lot of information on how that evolves. So in a lot of this work, I assume the literature ratio. And if you look at chemical models where with varying parameters, you do see a wider range of values, but it's unclear yet through observations exactly what we should be using for this type of environment. Okay, so can we find large-scale OH emission in Andromeda? It seems like yes. So after 20 hours of pointing the GBT towards the magenta pointing I showed you earlier, I found this. So this was a very nice detection of both main lines in OH. So this is moved to 4 kilometers a second. The peak H1 is about 30 Kelvin here. And the velocity width of the OH is very similar to the H1 velocity width, which is what we see in the Milky Way as well. The ratio of the profound intervals are in the 5 to 9, and we don't find a 1720 megahertz detection, which also probably implies LTE, because if you were to divide the 1667 profound interval by 9, you would get something buried in the noise. So that makes sense. It seems like this is a thermal detection. Here is the data just as a spectrum. This is taking the data in GPT-IDL, doing a 4th order polynomial fit, because so in this case, we didn't need high order polynomials because the velocity width is much, much lower than the velocity width in the outer galaxy of the Milky Way. So we could actually do pretty normal baseline fitting. And you can see the 1667 line here and the 1665 line to the right, around 350 kilometers a second. Now here I'm showing the non-detection on the right panel. Basically, in the paper that I submitted, I argue that the non-detection is actually probably something that we should have expected, because the H1 is about 3 times weaker here. And so as you probably realize in the earlier slides, it seems like the OH and H1 correlate very well in both velocity space and in brightness temperature. There's actually also a very nice correlation with some scatter. And so it kind of makes sense here that we don't find any OH, but it's also a nice confirmation that the actual detection isn't something in the spectrometer or the instrument that is introducing an erroneous signal. And so you can play the same game here by converting the OH, then the CO spectrum and the H1 spectrum to a column density of protons. And you also see that, with varying assumptions for the excitation temperature for the OH, the OH in this pointing does seem to be about equal to the H1 mass. Go. So the key takeaway here that I want you to leave with is that sensitive measurements of OH could trace the CO dark molecular gas in emission, and it's pretty much everywhere in the outer galaxy. We should think of this as being a major diffuse molecular phase of the ISM that's also partially atomic. It's probably well mixed with the CNM, and it definitely needs more studies with more tracers than just CO. And hydride seem particularly good. I'm not talking about CH in this talk, but there's also a lot of work done with CH that seems to be a good tracer for the dark gas. Modern single dish telescopes seem to be able to observe large scale faint OH. So Parkes also has a nice instrument now that can observe OH and CH at the same time. The GBT I've shown can trace it. The GBO's 20 meter can trace it. I believe the DRAO's 26 meter can also trace it. Effelsberg probably has a receiver that can trace it. So there's a lot of telescopes out there that can probably do this work. But in my opinion, we probably need something like FLAG or a phased array feed or some multi-beam instrument to trace to actually use the 18 centimeter OH lines as a good galactic tracer of dark gas, because for 20 hours, for one beam, it's probably going to be a prohibitive amount of time. So in order to alleviate that issue, you'd like something like a multi-beam instrument in the future. Okay, I can stop there, Jay.
Thanks very much, Michael. It's been a fascinating talk. And please submit questions using the Q&A button on the lower right. And I have one just to begin with is, can you say something about the sort of the physical structure of OH? You say it's mixed in, well mixed, but what exactly does that mean?
It's a very great question. Unfortunately, because, let's see. Unfortunately, let me go to this one. So, unfortunately, from the spectrum, we actually answer that question very well. So either that this is a volume, it appears to be volume filling, but it's unclear to me whether this is very tiny cloudlets of OH, or that there's a very diffuse continuous distribution of OH. I think that's what you're asking, right? And it's hard to answer that question. There's some information to be gleaned here from the differing angular resolutions. So as you go to higher angular resolutions, actually the brightness temperature of this feature becomes higher than the GBT. So that seems to me to indicate that this is you're having more of the source in a larger beam. Does that help?
Okay. We have some questions coming in. If OH and H1 correlate well in the diffuse interstellar medium, and you don't know the ratio of OH over H, what do OH observations really add?
So we know the ratio. So the whole point of the OH observations is to show that there are molecules out there, right? OH and CO are both molecular tracers. So you don't see CO a lot of the time outside the solar circle. And I mean, we know observationally what the ratio between OH and H2 is. It's pretty tight around this line here. So I mean, if you have an NOH of 10 to the 13, which is what I normally see, you can kind of say that you have an N to the H2 of 10 to the 20 with some scatter. It's unclear to me that in the really diffuse molecular medium that I see that this large diffuse galactic structure that this abundance ratio is true. It might change by an order of magnitude or two, but it's still showing that there's a lot of molecular gas out there not traced by CO. So that's what the OH adds.
Mm-hmm. Okay. Another question. How do you know that the CO dark OH gas isn't being excited by hydrogen rather than H2?
That's a good question. I assume the question is about collision excitation. I think they're both think both collisions are probably important. I'd have to think about that more. But I guess the answer is I don't know, but I would have to think about that more, yeah.
Okay. Another question, can anything be said about potential molecular water, H2O, existing in the OH environment?
Oh, something probably can be said, but not by me. I've been asked this question before. There's been conversations about like freeze out on grains, but in this diffuse molecular environment, you expect the environment to not be as cold as a traditional molecular cloud, right? So you're probably looking at something like 50 to 200 Kelvin for the temperature. And if you can't get like freeze out there, then it's probably not going to occur. But it's not my expertise, so I would have to talk to someone who actually knows that.
Okay. Another question. Carbon and oxygen have somewhat different origination than stars, and at very low metallicity, there may be more oxygen than carbon, whereas at higher metallicity, most of the O may be incorporated into CO. So perhaps your conclusions are very sensitive to metallicity.
That sounds more like a comment, but yeah, I would totally agree. One of the things about, so going towards the outer galaxy, there's definitely a metallicity gradient that it's unclear to me how that affects the NOH, but like you said, it does, it should, right? In the pointing towards M31, that pointing actually has pretty much solar metallicity. So I'm more likely to believe the abundance ratio there.
Okay, thank you. I have to identify the next person who's asking the questions because it's Isabelle Grenier. And she in many ways got this entire field started. And I must say to you, Isabelle, I was somewhat skeptical at your original work, and I now apologize for any skepticism that I might have had. She asks, whereas H1 and OH lines seem to cover the same velocity range, the H1 and OH mass do not correlate well spatially because we see different arm-to-arm peak ratios in the spectra. Have you looked at the variations of the mass of H1 over the mass of OH, or the mass of H1 over the mass of dark 2 from one arm to the next?
Mm-hmm. That's a very good question. I would have, no, I haven't. And that's a very interesting thing that I should do. One of the things I would say that the different arm-to-arm peak ratios, it might be affected by the H1 opacity too. If it's optically thick, then as I said, like OH and H1 correlate quite well, but there is a point where H1 just becomes optically thick above 60 Kelvin and the relationship basically stops. So we would have to look at just the optically thin H1 to answer that question. But yeah, we should do that.
Okay, another question. What do you estimate as to the relative mass contributions of H1, CO, H2, and other gases in gas clouds in the Milky Way?
It's a good question. So they're all basically relatively the same to each other. There's H2 is traced by CO. So I assume that's what you mean by CO. The content is traced by H1 is about the same as the dark H2 is traced by OH. And so it just seems like you just multiply everything by 2. It seems like there's a factor of 2 here missing in the total the total baryonic mass of the galaxy in terms of H1 and CO. So it's actually like a few percent in terms of the total baryonic mass. So it's not, don't get too worried.
Okay. There's a comment that water is hard to observe at 0 redshift. But another question as well. Do you have any evidence of OH self-absorption in the same way that H1 is self-absorbed?
So far, no. And it might have to do with the fact that OH is always optically thin. But yeah, so far, no.
Okay. Well, that's been a very lively discussion. And I would like to thank you, Michael, for your presentation today. Quite interesting. And remind everyone that we are meeting again 2 weeks from now. And I don't have the actual schedule up with me, but it is on our website. And so I look, oh, wait a second, one last question came
Yeah,
in.
I was about to say. Go
Do you
ahead.
think that there's a lot of gas that emits an OH, but contains CO that is not excited into emission? This could be checked by CO absorption toward extragalactic sources.
I think that is exactly the case. And I think that this observation should be done. I think, so I have a conjecture that basically that as you go out towards very large galactic radii, that the volume density is getting quite low. And even though there might still be CO there, the CO is just not collisionally excited. And so it's just an idea I have. It's not actually, I haven't actually proven this, but I think that type of observation could be very instrumental in showing that.
Okay, thank you very much, Michael. And we will look forward to seeing everyone here 2 weeks from now. And the topic, as I said, is on the GBO website. I don't have that right in front of me now. But thanks and goodbye.
Thank you, everyone.